Hello students, I am Isha Mandarata. In today's video, I am going to discuss numericals of semiconductors. Let's start. So the first numerical says that for an intrinsic silicon, intrinsic means it's an intrinsic semiconductor, or I would say a pure silicon which doesn't contain any impurities. So the electrical conductivity is given as 4 into 10 raised to minus 4 mho meter inverse, or you can say ohm meter inverse. The electron and hole mobilities are given. So mu e and mu h are given. You have to find out electron and hole concentration at room temperature. It's an intrinsic semiconductor, and we know that for intrinsic semiconductors, Ne, that is number of electrons per unit volume, and Nh, that is number of holes per unit volume, are the same. And the law of mass action says that intrinsic concentration is equals to Ne, that is Ni is equals to Ne is equals to Nh. So let's start. So we have the equation sigma I, that is conductivity, is equals to Nie mu e plus mu h. This is the equation which defines the conductivity of intrinsic semiconductor. So I can write that. Now we have been given electrical conductivity in the numerical in the question. So I can write Ni is equals to sigma I E mu e plus mu h. Sigma I is 4 into 10 raised to minus 4 upon charge of electron, that is 1.6 into 10 raised to minus 19. Mu e is given as 0.14 plus 0.40. So solving this, I get the value of Ni as 1.38 into 10 raised to 16 atoms per meter cube. Now, as I said in the beginning, that by law of mass action, because we are given room temperature also, so according to law of mass action, Ni equal to Ne equal to Nh. So I can simply write Ne is equals to 1.38 into 10 raised to 16 electrons per meter cube, and Nh is equals to 1.38 into 10 raised to 16 holes per meter cube. Clear? Let's move on to one more category, which says for intrinsic semiconductor, the carrier density at room temperature in germanium is 2.37 into 10 raised to 19 per meter cube. Electrons in hole mobilities are 0.38 and 0.18 respectively. You have to find its resistivity. Which formula you will use? We use the equation of conductivity, because we know the relation between conductivity and resistivity, that they are inverse of each other. So I have sigma I is equals to Nie into bracket mu e plus mu h. But I have to find resistivity. So I can simply write rho I is equals to inverse of this. So 1 upon N into E mu E plus mu H. So this is nothing but 1 upon N is given as 2.37 into 10 raised to 19. Charge of electron is 1.6 into 10 raised to minus 19 into we have mu E, that is 0.38 plus 0.18. Solving this, we have rho is equals to 0.471. Unit of rho is ohm meter. Clear? Let's move on to one more type of numerical, which says that suppose the effective mass of holes in a material is 4 times the mass of electrons. So you have been given the relation between Me and Mh. At what temperature the Fermi level should be shifted by 10% from the middle of forbidden gap if the gap is 1 electron volt. So in this numerical, you are given that Me and Mh are related by a relation. The relation is given. You have to find out the temperature at which the Fermi level is shifting By how much? By 10%. From where? From where it is shifting by 10%? It is shifting from the center. Now you know, always at 0 Kelvin, the Fermi level is exactly in the middle of forbidden band. So what I have to do here is, first let me write down the equation which I'll be using. And before that, according to the given question, the mass of holes is equals to 4 times the mass of electrons that is given. And you are given the value of Eg as 1 electron. So this is given in the question. Now I know the equation of EF. EF can be written as EC plus EV by 2 plus 3 by 4 kBT ln of mh star by me star, where this mh star and me star just denotes the effective mass of an electron and hole respectively. Now, before I start this numerical, I would just like to draw the graph and then explain it to you before we start solving. So what I consider is, I'll just consider this as temperature axis and I'll just consider this as the energy axis. So here I can just say that this temperature corresponds to 0 Kelvin. I am given the value of Eg. Suppose I say this is EV. Suppose I say this is EC. So I have been given this value as 1 electron volt because difference between lowest of conduction and maximum of valence is Eg. So at 0 Kelvin, this is the value of EF. I'll just draw a dotted line. Now we have to find out the temperature at which this is rising by 10%. Suppose this is 10%. So you have to find the corresponding temperature in Kelvin. Understood the question? So what we are going to do here is, can I just say that at the temperature 0 Kelvin, I have the value of EF as, what is this? This distance is EV. And what is this distance? 0.5. So can I write at 0 Kelvin? I'm just writing over here at 0 Kelvin. So I say at 0 Kelvin, I can say that EF is equals to EV plus 0.5. Also, I can use this equation and write EF is equals to EC plus EV by 2. Why? Because the temperature term becomes 0. So I'll just compare these two equations and I have EC plus EV by 2 is equals to EV plus 0.5. Suppose I say this is my equation number 1. Now you have to find a temperature at which your Fermi level is rising. Suppose I say this is my temperature which I need to determine. At this temperature, Fermi level has shifted by 10% from the middle. So 10% is 0.1. So 0.1 from the middle, in the sense it has shifted like this. So I can say this is EV plus this is 0.5 plus this is 0.1. This is somewhere the position of my Fermi level. So what I can write as, I can simply say that at temperature greater than 0 Kelvin, so when T is greater than 0 Kelvin, my EF would be EV plus 0.5 plus it has shifted by 0.1. This gives me 0.6 electron volt. And because the temperature is not 0, the equation of EF remains the same. So I can just write that EV plus 0.6 is equals to EC plus EV by 2 plus 3 by 4 kBT ln of mh star upon me star. Getting it? So say this is my equation number 2. Now I will subtract equation 1 from equation 2 and I get 0.1 is equal to 3 by 4 ln of mh star upon me star. This is nothing but ln 4. But please remember this 0.1 is an electron volt, so we need to convert it into joule. This is kBT. So I can just write 0.1 into 1.6 into 10 raised to minus 19 is equals to 3 by 4. Value of kB is 1.38 into 10 raised to minus 23 into ln 4 into T. So this t we need to determine, and I'll just take all the data on the left hand side to find out t, ln of 4. So all the data, so t will be 0.1 into 1.6 into 10 raised to minus 19 into 4 upon 3 into 1.38 into 10 raised to minus 23 into ln 4. So solving this, we get the value of t as 1115.2 Kelvin. This is how you need to do. So for such numericals, whenever such a type of data is given, just try to draw the diagram or just imagine it in your mind and then solve. It would be easier to solve. Now let's move on to one more type of numerical. So the question says you have to find resistance of an intrinsic germanium rod which is 1 centimeter long, 1 millimeter wide, 1 millimeter thick, and the temperature is given as 300 Kelvin. You are given the value of Ni, mu h and mu e. So I'll just start. I just want to say here that the value of, so this is nothing but mu e. Okay. So we have to find R. You are given all the dimensions. How do you find out resistance? So I just write sigma I is equals to Nie mu e by mu h. Why do I find conductivity first? Because I know the relation between conductivity and resistance, and I have been given this data. So this is Ni is given as 2.5 into 10 raised to 19. This is 1.6 into 10 raised to minus 19 into bracket mu e, that is 0.39 plus 0.19. So this gives me the answer of sigma I as 2.32 mho meter inverse. Now I know that R is equals to rho into L by A, or I can say it is L upon sigma A, because I know rho is equals to 1 upon sigma. Now what is L given here? So L is equals to 1 centimeter, that is 10 raised to minus 2 meters. Also area is equals to width into thickness, so that is 10 raised to minus 3, because 1 mm is 10 raised to minus 3 into 10 raised to minus 3. So A is 10 raised to minus 6 meters square. Please do the conversions properly. So now I'll write R is equals to L, that is 10 raised to minus 2 upon sigma, that is 2.32 into 10 raised to minus 6. So this gives me the answer of R as 4310 ohm. I hope this is clear. Let's discuss one more numerical. At 20 degrees Celsius, conductivity of germanium is 2 ohm meter inverse or mho meter inverse. Find the conductivity of germanium at 40 degrees Celsius if the band gap is given to you. Which formula you'll use? You'll use the equation of conductivity, not with intrinsic concentration, because that is not given. You are given the conductivities at two different temperatures. So we'll be using the formula. You will be using the formula sigma is equals to C into e raised to minus Eg upon 2 kBt. Clear? So I can write this equation for two different temperatures. So for suppose I say conductivity at sigma 1. So I'll be writing conductivity sigma 1 for temperature T1, conductivity sigma 2 for temperature T2. Kb will be constant, Eg will be constant, and 2 is a constant. So what I do is I just directly write the equation. So I'm just writing sigma 2 upon sigma 1. C is a constant, it gets cancelled. This will be equal to e raised to minus Eg upon 2 kb is a constant. You have 1 upon T1 minus T2 minus 1 upon T1. Or what do I do is I just remove this sign. Suppose I convert this as 1. So this will be minus and this will be plus. So it's 1 upon T1 minus 1 upon T2. So this can be written as e raised to Eg upon 2 kb T2 minus T1 upon T1 T2. Clear? What is Eg given to you? So Eg is given as 0.7 eV, but we have to convert it into joules. So 1.6 into 10 raised to minus 19 upon 2 kV. So 2 into 1.38 into 10 raised to minus 23. This is into T2 minus T1. So what is T2? 40 degrees Celsius, but please convert it into Kelvin. So 313 minus 20 degrees Celsius is 293 divided by 313 into 293. So you will get the value of sigma 2 by sigma 1, 2.484. Clear? So we have to find sigma 2. So that is 2.484 into 2. So sigma 2 is 4.96 mho meter inverse. Clear? Because it was the question did not contain the intrinsic carrier concentration, and instead of it, two different conductivities were given at two temperatures, we use this equation. Let's see one more numerical. In p-type germanium, intrinsic concentration is 2.1 into 10 raised to 19 per meter cube, and density of boron is 4.5 into 10 raised to 23 atoms per meter cube. Electrons and hole mobilities are 0.4 and 0.2 respectively. You have to find the conductivity before boron is added and after boron is added. So before boron is added, we'll be using the formula sigma I is equals to Nie mu E plus mu H. So I get Ni is 2.1 into 10 raised to 19, 1.6 into 10 raised to minus 19, and 0.4 plus 0.2 is 0.6. So sigma I get is 2.016 mho meter inverse. This is before boron is added. But what will happen if you add boron? If you add boron, which is a trivalent impurity, your germanium will behave like a p-type germanium having holes as majority carriers. And in that case, sigma I can be given as N of boron, number of boron atoms added, because the number of boron atoms added will be equal to the number of holes which are created in valence band, into E into mu H only. Why not mu E? Because electrons are minority in case of p-type semiconductors. So now what is given in boron? Number of boron atoms are 4.5 into 10 raised to 23 into charge of electron is 1.6 into 10 raised to minus 19 into mobility of hole is 0.2. So you get the answer of sigma I as 1.44 into 10 raised to 4 mho meter inverse. Just compare the two values. Temperature is the same, room temperature. When boron is not added, conductivity is only 2.016. But if you add boron atoms, the conductivity has drastically increased. That is the reason we dope semiconductors. Clear? Let's see one more numerical. This numerical says that a semiconductor material crystal 12 mm long, 1 mm wide, 1 mm thick has a magnetic flux density of 0.5 Weber per meter square. It is applied from to back and is perpendicular to the largest faces. When a current of 20 milliamperes flows lengthwise through the specimen, voltage measured across its width is 37 microvolt. You have to find out the Hall coefficient of the semiconductor. So this is a topic which is related to Hall effect, wherein current is through the semiconductor, perpendicular magnetic field is applied and voltage across the width is measured. That is Hall voltage is measured. We have to find out RH. Now, first let me write down the data. So length is given as L is equals to 12 into 10 raised to minus 3 meters. Width is 10 raised to minus 3 meters. Thickness is also 10 raised to minus 3 meters. Flux applied is 0.5 Weber per meter square. Current is 20 into 10 raised to minus 3 amperes, and Hall voltage is 37 into 10 raised to minus 6 volt. Now you know the equation between Hall coefficient and Hall voltage. So VHT upon I into V. So VH is 37 into 10 raised to minus 6. Thickness is 10 raised to minus 3. Current is 20 into 10 raised to minus 3 and B is 0.5. So this gives us the answer as RH is equals to 37 into 10 raised to minus 6, and we know the value of RH, it is equals to 1 upon NE, because we have to find out the density of charge carriers also. So I can write this equation as, I can simply write N is equals to 1 upon RH into E, that is 1 upon, the value of RH is 37 into 10 raised to minus 6 into 1.6 into 10 raised to minus 19. So this gives us the value of N as 1.68 into 10 raised to 24 unit is atoms per meter cube. So in today's video, we have seen different categories or different varieties of numericals related to semiconductors. So I just hope that you have understood all the numericals I discussed today very well. Thank you.